Hi everyone, this is Dr. S. Today's lecture, chapters 10 and 11 on chemical reactions and solutions. As you can see, will be done asynchronously as we all voted on a week or two ago. And I will be keeping this video on YouTube for future reference. So by all means, you can pause, you can come back and revisit if there are any bits that are still confusing to you. And of course, if that doesn't clarify things, by all means, reach out to me and we can set up an office hours appointment to clarify, or just find me during lab. Okay, the core concepts and learning goals for today's lectures are the 4 items. The first thing that you should be able to do by the end of the lecture is to recognize the ionic or covalent nature of a molecule based off its molecular structure. And to that end, once you have a feel for the relationship between a compound's formula to its molecular structure, we can use that to really understand and identify the basic reaction mechanisms that we can expect for, in a chemical equation. These are going to cover the first half of the lecture. The second half of the lecture, which really concerns solutions of compounds, really is going to be understand how ionic versus covalent molecules would behave in a solution, because they won't behave identically, and also being able to predict the changes that a solution would experience depending on what is dissolved into it. Okay, so let's get into the meat of this. In the last lecture, we ended off introducing the concept of ionic versus molecular compounds, or ionic bonds versus covalent or molecular bonds. And to just really briefly recap, an ionic compound, which is also known as a salt, let me just turn on my pen here. So ionic compound, also known aka salts. These are formed when a metal element and a non-metal element ionize each other. So if you recall something like chlorine, it's going to have 1, 2, 3, 4, 5, 6, 7 reactive electrons in that outermost valence shell. And a metal like sodium, it's going to have 1. All right? And because we want the octet rule to come into play, where everything needs to have basically 0 or 8 electrons in its outermost shell, that chlorine is going to, oops, I forgot to draw that 7th one. It's going to steal that electron, okay? And it's going to make this a non-metal ion, and it's going to make this a metal ion, positively charged, negatively charged. We gain a negative electron, and we lose a negative electron, hence the positive charge. And consequently, when we do this, we're going to form sodium chloride salt, NaCl, solid, like this. And that electrostatic attraction between these two entities, that is the ionic bond, okay? Now, this is a bit of a simplistic picture. Something to know about ionic compounds is that they do not have, they lack a discrete unit or molecule. So a better way to really look at this is in this picture over here. So this is like a cartoon model of a sodium chloride salt. And the chlorides are these green balls, the bigger ones, and the sodium is the smaller purple ones. And it's sodium, it's chloride, sodium, and it repeats, okay? So the ratio of sodium to chloride is 1 to 1, but there is no like sodium chloride molecule. It is a lattice that goes on, indefinitely, as big as the crystal exists. And if you look, this is like an electron micrograph from like an electron microscope, this picture. Oops. All right. And this is one salt crystal. This is one molecule, so to speak. Salts don't really have molecules per se, they have crystals. But this is, one network of sodium chlorides bound together. All right, so when we write down the formulas for ionic compounds, what we're really doing is we're using something called the empirical formula, all right, which is not a true molecular formula in the sense that a salt doesn't have one sodium and one chloride, but rather it has one sodium for every chloride. It just shows the ratio between the two. Calcium chloride is going to be one calcium for every two chlorides, all right? And that's because calcium has two reactive electrons, and it can give one of these to each a chloride, okay? Covalent compounds, this is probably what you really think of when you think of molecular formulas. So to rehash, covalent compounds, that's usually comprised of only non-metal elements, okay? So like in this molecule down here, where's my cursor? In this molecule over here, it's going to be, carbons, hydrogens, and oxygens. These are all non-metals, and this exists as a discrete molecule, okay? And you express the chemical formula as the number of each atom in one molecule, and we call that the molecular formula. So this is a molecule of glucose. So what would the molecular formula for a glucose molecule be? It has three elements in it, we can see. It has carbon, just deleted that, carbon, hydrogen, and oxygen, CHO. Well, how many of each does it have? The carbons are black. I count 1, 2, 3, 4, 5, 6 carbons. And we're going to put a subscript 6 over here to show that there's 6 carbons in this formula. The hydrogens, there's more of those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. And how many oxygens? Those are the red atoms. 1, 2, 3, 4, 5, 6. C6H12O6, okay? Notice that the molecular formula is not an empirical formula. The empirical formula, which is that simplest integer ratio of all the elements, if I were to apply that to the glucose molecule, that would be CH2O. We don't show a 1 if that's there because it's implied. That would be the empirical version of glucose, and that's really not useful in our everyday discussion of covalent compounds. So don't really worry about that. Really just focus on the takeaway here is that for a covalent molecule, use the molecular formula, the exact number of each element in one molecule, because one molecule of glucose will be identical to another molecule or any other one in a sample. And for ionic compounds, well, you're going to use an empirical formula because ionic compounds exist as a giant crystalline matrix of repeating units. So no discrete single molecular entities. Okay, so another way to represent what a compound is using chemical notation is the structural formula. And this is a really useful tool because it gives you a hint as to what the arrangements of the atoms are within a molecule, which will give you a sense of its 3D structure. All right, it's more work to make a structural formula, but it'll give you a lot more information. Let's take a look at water, for example. H2O is the molecular formula, okay? That certainly tells you what elements compose the molecule, but if you look at a space-filled model or a line structure model, this will reveal, that water has a slant, bent geometry to it, and that the oxygen is in the middle of two smaller hydrogen atoms, and a really skilled chemist will be able to look at the structure of a compound and be able to make predictions and inferences as to what the properties of that substance would be. Okay, take a look at hydrogen peroxide for comparison. It's similar to water in the sense that they're both composed of hydrogens and oxygens, but the shape of the molecule is very different. You get this slanted structure for hydrogen peroxide compared to the bench structure of water. And that is going to have some pretty big effects on the properties of them, that, you can't drink a glass of hydrogen peroxide and expect to be, okay later that day. So there's a lot of information within the structural formulas. Another boon to knowing the structural formula for a compound is that it can alleviate some ambiguities. All right, it delineates structural isomers of a compound. So isomers, what is that? An isomer is basically two compounds that have the same formula, but they're completely different entities. So this compound over here, dimethyl ether, it is a gas. It used to be used as an anesthetic, but it's actually quite toxic. So modern medicine has grown to use more reliable anesthetics. And it has an oxygen atom sandwiched between these two, what we call methyl groups, carbons with a bunch of hydrogens on them. Also, C2H6, one oxygen, is ethanol. Ethanol you may more likely have had experience with. This is the scientific name for, alcohol, drinking alcohol specifically, all right? The difference between dimethyl ether and ethanol, of course, is that the oxygen is, kind of on the outside of this molecule, and it's going to completely change its properties and its physiological and metabolic effects upon, consumption. And, you really can't tell the difference between these two compounds just by going off the molecular formula alone. So structural formulas, they're pretty handy. Okay, now we're going to be discussing molecular and formula weights. And these words can be used interchangeably, molecular and formula weight. Basically what they are, it is the sum of the atomic weights of all atoms in a chemical formula. So if you don't have one open in front of you now, either in a separate browser tab, or I recommend, printing out a periodic table or opening it in your textbook, have a periodic table in front of you for really the rest of this lecture, because we will be referencing it sporadically throughout the lecture. So pause the video and give yourself time to have one in front of you for you to reference, or you could print it out from the internet, I don't care. Now that you have a periodic table in front of you, take a look at, I don't know, let's take a look at the carbon element square. It'll be on one of the top rows. So that is going to look, it's hard to draw straight lines on this thing, so bear with me. It will be the sixth element, so it will have a 6 at the top of its element square, denoting that it is the sixth element. And the chemical symbol is going to be C, and underneath it, it's going to have the number 12, like 12 point something. I think it's like 12.00 something. This is the atomic weight of carbon, which means that 1 mole of carbon equals 12 grams, 12 point whatever grams. It will also mean 1 carbon atom has a weight of 12 point whatever Daltons, or atomic mass unit. Same thing. So a Dalton is the weight of, pretty much a proton. So it's going to be a very, very small measurement of mass, but there's a relationship here, which is very intentional and convenient. All right, so this is just to review how we get this information out of the periodic table. And different elements are going to have different atomic weights. So different compounds formed of different elements are all going to have different molecular weights. And you can sort of get a visual appreciation of that in this picture over here. We have a dish full of sucrose over here. we have a vial of water, a vial of mercury, sulfur is an element. This is called potassium dichromate, this orange, beautiful cancer-causing substance, sodium chloride, copper, and lead. Now, these are all different visual amounts because their molecular or atomic formulas are all going to be different, which means that 1 mole of each of these entities will correspond to a different amount of mass. So let's apply this over here to some more elevated examples and determine the molecular weights of these two compounds. So the first we'll do is road salt. This is what they put on the roads to make them more drivable in icy weather. Calcium chloride. They don't use sodium chloride, they use calcium chloride, I believe. And this is an ionic compound, but the same rules apply. You know, what is the repeating unit here of a calcium chloride crystal? What is the molecular weight of that? Well, open up your periodic tables and consult the calcium and the chloride element squares. Now, I just happen to have memorized the calcium and chloride atomic weights because I use them frequently in my day-to-day work, but 38 atomic mass units or grams per mole is the atomic weight of calcium. And you can double check me on that because maybe my memory is wrong, but I doubt it. For chlorine, it's 35, come on, 35.45. I should do that. 35.45 for chlorine. We have 1 calcium atom and calcium chloride unit, but we have 2 for chlorine. So 38 times 1 is going to be 38. And 35.45 is going to be what? 70.9. So let's add those together. 38 plus 70.9. That is going to be 108.9. 100, I'll write it up again over here. 108.9 grams per mole of calcium chloride, or 108.9 Daltons per 1 unit of calcium chloride. The next example we can work on is table sugar, sucrose. This is a bigger molecule. It's also a covalent molecule because there's only non-metals in it. And we have carbon, hydrogen, and oxygen. Well, I told you just now that carbon has a molecular weight of 12 Daltons or grams per mole, about. Oxygen, consult your periodic table. You know, I'm going to give you the answer in a second, but I'd rather you develop the skill of figuring it out for yourself or determining it for yourself. So the atomic weight for oxygen is going to be 16. And hydrogen is pretty easy. It's going to be 1. Now let's multiply each of these by the subscript in the molecular formula, which will tell us how many of each element is in one compound. So carbon is 12. We will multiply that by 12 for the 12 carbon atoms in that sucrose molecule. Oxygen, that looks like a V. Oxygen has 16. No, excuse me. Its atomic weight is 16, but it has 11 atoms in it. All right. Hydrogen is going to be 22. So if you multiply that all together and then you add them up, you know, I want you to practice your multiplication skills right now. Do it out by hand, tally them, and see if your answer tallies up to 342. That is the answer for the molecular weight of that's the 342 grams per mole for 1 that's how many grams are in 1 mole of sucrose, 342 Daltons in 1 compound of sucrose. Okay, now another form of data that we can extract out of a molecular formula is the percent composition by element, which is to say, what percent of this element composes a given molecule or a mole of that molecule, and what is the percent composition of, the other one or all the rest. And there are many uses for this, but let's just use sodium fluoride as an example question for you to practice on. Sodium fluoride is an additive to a lot of toothpastes, and that's because the fluoride will combine with your teeth in a way to make them resistant to decay. And in this question, we are asking you, get my pen ready, we're asking you, that's a highlighter, we're asking you what percent composition of a sodium fluoride salt is sodium and what percent composition is the fluoride by weight. And at first this seems kind of maybe daunting or intimidating, but I promise you it's not hard when you break it down into these 3 steps, which is to write down the formula, determine the molecular or formula weights for that compound, and then you calculate the percentages of each individual element over the whole. And I'll walk you through that process, and you'll see that it's not as bad as you probably are making it out to be. So, okay, what is step 1? Write the formula for the compound in question, sodium fluoride. We know that it's going to have the element sodium and the elements fluoride, all right? But what's the ratio between these 2 elements, all right? So consult your periodic table and tell me how many reactive electrons they have. We know that sodium is in group 1, so it's going to have 1 reactive electron. Fluorine is in group 7, so that means it will have 1, 2, 3, 4, 5, 6, 7. Okay, we need to add up electrons until someone has a happy 8 according to the octet rule. And it just so happens that fluorine can take 1 electron from sodium to satisfy the octet rule. So the molecular formula is just sodium fluoride. That's all. Pretty easy. Now we will determine what the formula weight is, and you will also have to pull up the periodic table for that. So again, I kind of just know this, but look at the periodic table and determine what the atomic weight for sodium and fluorine are. I happen to know that sodium is 23 atomic mass units or grams per mole of sodium. Fluorine is going to be 19. All right. So since they each have 1 atom represented in the molecule, it's going to be a total of 1 times 23 and 1 times 19, which is just themselves. And the formula weight for 1 sodium fluoride unit, you really can't say molecule because it's a salt, is going to be 42 Daltons or 42 grams per mole. Okay, good. Now, what percent of that 42 grams per mole is attributed to mass by sodium versus mass by fluorine? So it's just a question of division, really. We are going to find, the parts over the whole. We know the whole is going to be, let's solve for sodium first. It's going to be 42 Daltons. 42 Daltons in 1 sodium fluoride molecule. Of those 42 Daltons, sodium composes 23 Daltons of mass. So 23 divided by 42 is going to give you like 0.54 something, 0.547, and you multiply that by 100% to get 54.7% sodium composition in sodium fluoride. We are going to do the same thing to solve for the percent composition of fluorine by listing at the bottom what the whole composition mass is, which is 42 daltons for one sodium fluoride molecule. But now we're going to divide it into the mass of just fluorine, which will be 19 daltons. You divide that, you multiply it by 100%, and that will give you 45.2%. Now, in theory, this should add up to 100%, right? But it's going to be a little bit off, a little bit shy of that. And that's really just because rounding errors, I'm using nice even numbers here. Really, the mass of sodium, I think it's like 22.99 or something like that. So, you just got to bear with the assumptions. Just make sure that you did this right. When you add up everything, it's close to 100, like within a percent off. Okay, these reactions are pretty cool. The next class is single replacement reactions, and the metaphor that I like to use to describe them are that these are homewrecker reactions. And an example of that is this copper chloride with aluminum reaction. And to break this down a little bit, what we're seeing here is an atom or ion that's within a compound is being replaced by a single atom or ion that's not in a compound. The general reaction scheme for this is xy plus z, where z is the homewrecker. And what that's doing is z is more reactive than y. So it is getting in there, interfering with the relationship, and kicking out y as the third wheel. And xz becomes the new compound form with y being liberated. And an example of that, a more concrete example of that, is this reaction of copper chloride and solid aluminum metal. So you see over here the aluminum metal, which is this. This is a solid element, and we're going to put it in a solution of copper chloride, which is blue. Okay, copper and water, copper ions and water look blue. Now, the aluminum wants to be with the chloride more than the copper. So what happens is we're going to displace or replace the copper from this equation, and we're going to be left with elemental copper. And we're going to form a colorless aluminum chloride salt. And elemental copper is like brownish, reddish brown. Copper ion in water is blue. And you can see here that we have the aluminum bar dunked into the blue liquid. This is copper. The copper mostly, well, it's black on black, but it mostly moved over here. Okay, that's elemental copper. That was taken out of the solution and deposited onto the site of the swap, which was the aluminum bar at the interface of the solution to the aluminum. So that's kind of cool to look at. You know, it's very dramatic. Okay, this is the last class of reaction, and this also is kind of a cool one in my opinion, the double replacement reaction. And this occurs when you have two compounds that interact with each other and they swap their partners. So if you had AX compound reacting with BY compounds, you would form AY plus BX. And the trick here to make this sort of work is that you need to form one of three different things as the product. It needs to form a solid precipitate that will crash out of the solution and prevents basically these partners from swapping back to their original partners. It needs to form an escaping gas, which will waft away, and then that would also prevent things from swapping back to the original configuration. Or it would react to form water, and we'll see an example of that at the end of the lecture, where water is a very stable compound and it's not going to react anymore, and that will also drive the reaction towards the products or to completion. Okay, and here's a really beautiful example of that. In this GIF, we have a solution of potassium iodide being added to a solution of lead nitrate. Both of these are clear colorless salts, and they form clear colorless solutions when dissolved in water. I should also mention that nitrates, NO3, this is an example of a polyatomic ion. All right. So polyatomic. which is basically, it's a compound with charge. So nitrate has a -1 charge. Lead, in this case, has a +2 charge. So this acts like a salt, even though there's a covalent compound in it. It's a covalent compound. So 2 -1s balances out the +2 of the lead. That makes it, a stable salt, even though it has a covalent component to it, which is kind of cool. Anyway, sorry for that aside. 2 potassium iodides react with 1 lead dinitrate, because there's 2 nitrates in that salt. It reacts and you swap the partners. The iodides go to the leads and the nitrates go to the potassium. 2 potassium nitrates form. These are super soluble, no color. Lead iodide is this beautiful yellow color, and it looks like a yellow liquid that's actually like a yellow fine dust that will settle into a powder over time. But that forms immediately upon contact with the solution, because this lead iodide compound is really poorly soluble, it turns out. So it's going to form a precipitate and crash out of solution, and it's not going to want to go back to the original lead nitrate and potassium iodide configuration. Lead and iodide love each other that much, they can't be separated, ever again in this scenario. And so this, again, is a very dramatic, kind of cool representation of a double replacement reaction. Okay, now chemical equations are useful because they are essentially the recipes for making a compound. This over here is the recipe, for example, for making ammonia, all right? We have 3 dihydrogen molecules reacting with 1 dinitrogen molecule to yield 2 molecules of ammonia, NH3. So one interpretation of this is that we have a representation of the molecular ratios of reactants to products. Said in plain English, this is how to make 2 molecules of ammonia. But let's face it, 1 molecule, 2 molecules of ammonia, even 1,000,000 molecules is too little to be useful. We want to make gajillions of molecules of ammonia to use, like a mole or two. A mole is 6.02 times 10 to the 23. That's a huge number. That's a lot of molecules of ammonia. But in real life, that's not going to fill, a bottle of Windex. But just to use this as an example, though, if we scale this up to the mole ratio, instead of saying 3 molecules of dihydrogen plus 1 molecule of dinitrogen, we could say 3 moles of H2 plus 1 mole of N2 yields 2 moles of ammonia gas, which is saying 3 times 6.022 times 10 to the 23 molecules. But since that's annoying to say, we just use moles as a shorthand. So that's a second possible interpretation of a chemical equation. It's the mole ratios of reactants to products. Well, that's, perhaps at a more useful scale. However, we really can't measure moles out directly. There is no mole machine or counter where we put something in and it says, we've got a mole of this stuff. No, we need to use the periodic table to infer how many moles are in a sample based off of the formula mass or the formula weight or the molecular weight. All right, moles are really useful for showing how equations pan out, but we have to measure the ingredients in, let's say, grams, because that's what our instruments are capable of doing easily. So said another way, look at your periodic table and tell me what the mass ratio of this chemical equation is. 3 moles of dihydrogen gas, we all know by now that 1 mole, the atomic weight of hydrogen is 1 atomic mass unit or Dalton or gram per mole. We have 3 dihydrogen molecules, that's 3 times 2 times 1 equals 6 grams, corresponding to 3 moles of dihydrogen gas. Nitrogen is 14 daltons, or atomic mass units. 1 mole of dinitrogen, multiply that by 2 to get 28 atomic mass units. Also grams per mole, same thing. So now we know if we measure out 6 grams of dihydrogen gas, we know we need to measure out another 28 grams of dinitrogen gas to react with the dihydrogen to yield 34 grams of ammonia. And we know 34 grams of ammonia will be produced every single time, assuming the reaction goes to completion, is because 1 equivalent of nitrogen is 14, 1 equivalent of hydrogen is 1, and we have 3 of it. So 3 plus 14 is 17, and oh wait, we have 2 moles. Multiply this by 2, and we get 34 grams per, not 34 grams per mole, but we get 34 grams in total. All right? So there's a lot of information that we can extract out of the chemical equation. Okay? That's why I spent so much time, discussing this and leading up to this point. This is one of the most important slides of the lecture. However, the hard part about chemistry is not just writing out this reaction and calculating how much product you'll get, and ta-da, then you make money when you sell that much ammonia to the Windex company. No. The hard part is really discovering the conditions and the temperature and the mixing times of the reactant substances to get the full, 34 grams out of the efforts that you put into setting up this reaction. And 99 times out of 100, the way that chemists get things to mix and react well is by dissolving them into the same liquid and using that as the way of mixing them and getting them to react. And that's going to compose the second half of the lecture, which is going to concern solution states of these entities. Now, something that you may already have an intuitive sense of is that solubility is a property that's unique to every solvent and every solute, and it is subject to change. So when you have let's say, water, and you are trying to make syrup, for example, if you just pour sugar into water, it's not going to really dissolve very nicely or very quickly. But if you heat it up, all that sugar goes into solution and it disappears. So that's an example of solubility changes. So the solubility of a compound, usually a solid solute, is going to increase as a function of temperature. So take a look at this graph over here. These are 4 different salt compounds: sodium nitrate, potassium chloride, and sodium chloride, which is table salt. Okay, so these blue lines represents the solubility of these different entities at a given temperature. And the solubility is expressed not as molarity. I figured you needed a break from molarity, but it's the grams of that solute dissolved in 100 grams of water. So they all start on the lower ends at very cold temperatures, so almost freezing. Potassium nitrate is a dramatic example. You can only dissolve 10 grams of it in 100 grams of water. You increase that to, room temperature, and it's going to be around 35 grams of potassium nitrate dissolved in 100 grams of water. That's more than triple. That's a huge increase. And you go even higher and the solubility just like goes through the roof. So this really is a nice dramatic example of how when you increase the temperature, you're able to dissolve more of something. Sodium chloride is like a surprisingly boring example of that. It barely goes up by like 1 gram, going from almost freezing to almost boiling. But these properties, as you can imagine, are unique to the different solutes. Now, as a slight caveat, the trend reverses for gases. So gases, pretty much in general, all have very poor solubility in water, but it's non-zero solubility. I I don't know how to do I can't do the conversion in my head very easily, but I know that, for example, that saline solution was 0.15 molar. Dissolved oxygen in water is like 0.25 micromolar. So it's like a million times less. That micro means a millionth of physiological saline. So it's quite small compared to solids. But get this, as you heat it up, the solubility of gases is actually going to decrease even more. And this is actually a problem in the context of global warming because fish gills operate by very efficiently extracting out dilute oxygen gas dissolved in water, and incorporating it into their body. As we warm our planet, the oceans get more warm, and that dissolved oxygen is actually going to outgas, and it's going to be less available for the fish. And in areas where there's like, near, for example, factories, they will pump in river water to cool down, bits of machinery and release that warmed water back into the river. Well, those factories are increasing the temperature of the water, and that's going to decrease the solubility of oxygen, and you get these massive fish die-offs, which really interrupts the ecosystem. So this is an example of how knowledge of solubility trends actually has an environmental impact. Okay, acids and bases. So you may recall from the previous slide that I told you that an acid increases the hydronium content in a solution, whereas a base increases the hydroxide content. So how do we go about achieving that? Well, we dissolve acidic or basic solutes into water that will react with water and change those ratios directly. So let's first talk about acids, because I feel like people are more familiar with those. Believe it or not, a lot of acids are often non-metal hydrides. So you take a non-metal like chlorine and you react it with hydrogen and you get HCl, hydrogen chloride, also known as hydrochloric acid. So this acid compound has a really weak bond between the hydrogen and the chloride. It wants to just fall apart, and water greases that wheel. When you dissolve hydrogen chloride into water, that water is going to attack and take that proton, all right, and it's going to form H3O, hydronium plus, with chloride negative as the leftover product, okay? And you can see that represented here as the molecular formula. H2O plus HCl yields H3O plus chloride negative, okay? So what we're doing here, to reiterate, we're donating a hydrogen ion, sometimes called a proton, to the water. Bases are the opposite procedure of that. So a common base is sodium hydroxide. This is lye, also known as oven cleaner. That's a horrible E. Lye. Common bases are metal hydroxides. So sodium hydroxide, potassium hydroxide. These are all really powerful bases. And what happens is kind of like the opposite to what we described in the acid process. We have sodium hydroxide, and instead of this, instead of it giving a proton to water, we're going to take a proton away from water, okay? And when that proton leaves, we're going to be left behind with a hydroxide ion, OH minus. And that hydroxide that was bound to the sodium hydroxide will become water in turn, because now it's going to have 2 hydrogens to 1 oxygen. And that sodium is not going to, be ionically bound to that water anymore, so it's just going to fall apart and you're going to get, sodium ion dissolved in solution. So you can appreciate how, acids and bases kind of behave oppositely to each other. Now, another way to think about acids and bases is that acids, when you dissolve them in water, donate a proton or a hydronium. But for this slide, we're just going to make it easy and just describe it as a proton, H+. Proton donor. It generates protons into solution. I use black. That was a mistake. The red means nothing. For bases, you're going to donate hydroxides when dissolved in water. Okay? So not only do acids react with water and bases react with water when you dissolve it in them, they also react with each other, and this is kind of cool. So let's predict, like a scientist would, the reaction products of HCl with NaOH, okay? So this is going to require a little bit of drawing, so just take your time and bear with me. HCl aqueous. And that parentheses AQ, aqueous, means that this entity is dissolved in water in this reaction, plus NaOH, sodium hydroxide, Li, AQ, also aqueous, dissolved in solution. It's going to react and it's going to form, something. We don't know quite yet. All right? So how do we figure that out? Well, I just told you that acids donate protons when they dissolve into water, and bases donate hydroxides when they're dissolved into water. So these are going to dissociate. We can think of it that way. We can split these apart. Remember, hydroxide is like a polyatomic, so we're not going to break the O and the H, we're just going to break the OH from the sodium, all right? But let's just write it out here. H plus proton ion, aqueous, plus chloride ion, also aqueous. That looks like 2 Q's, but that's an A. Plus sodium ion, aqueous, plus OH ion, aqueous. And what could this react to form? So what are the ways that we can combine these 4 entities? We could recombine sodium with the hydroxide and the proton with the chloride, but acids don't have a strong affinity for their protons. They like to donate those, so that's not going to happen. And hydroxides, don't have a strong bond to their metal ions, so that's really not going to happen either. Would the chloride react with the hydroxide? No, that wouldn't happen, because the chloride, that's going to be negatively charged, and that's not going to want to hang out with the negatively charged hydroxide. Same goes for the sodium and the proton. That's not going to react with each other. All right, well, what's the only other option? We could, however, have the sodium react with the chloride and form sodium chloride, aqueous. Plus, this is kind of interesting, hydrogen hydroxide, HOH. There's got to be another way we can phrase that. Hydrogen hydroxide sounds kind of strange. Let's just call it water, H2O. What you just witnessed is a neutralization reaction. And this is just like a reaction class we saw in the first half of the lecture. Specifically, it's a double replacement. I use a lowercase d and a capital case R. That was kind of silly. But still, it's a double replacement reaction. where the HCl and the NaOH swaps their partners to form salt and water. And this is actually a really good thing to know because we took two really powerful substances, hydrochloric acid and sodium hydroxide. We reacted them with each other and we made a very tame and not dangerous salt and water. You stick your hand in a solution of either of these and you're going to pull back bones, if they were concentrated enough. But salt and water are very innocuous. There's really important safety ramifications to this. So I've spent, over 10 years working in the lab, and it's bound to happen. You're working with some acids and you get some on your hand. What's a really useful remedy is to apply, a basic solution to that to neutralize the acid before it eats through your skin. So it's a good skill to know that acids and bases are dangerous, but they can be tamed if you have a solution of neutralizer, at hand. All right, the last thing we're going to talk about is the pH scale, to expand upon the concept of a power of hydrogen, which we mentioned a few slides ago. So we defined neutral pH as the pH where the proton concentration, or the hydronium concentration, equals the concentration of hydroxide. And that happens when it's, 1 times 10 to the minus 7 molar hydronium or hydroxide. Written another way, 0.123456 molar hydronium or hydroxide. This is really annoying to write out. So that's why we use scientific notation, 1 times 10 to the negative 7. But even this is a lot of 1 times 10, 1 times 10. So scientists came up with the pH scale, which is called a logarithmic scale, which means it's all based off exponents of 10. So what we're doing here for the pH scale is we're just focusing not so much on even the negative part, but we're just going to focus on what this number is. So when we say the pH is 7, the power of hydrogen is 7, we mean that it is 7 decimal places out until we get our numerical measurement, until we get the reading of 1 molar, of 0.00000001 molar, all right? So something that would be, you know, 1,000,000 times more concentrated of hydronium, or 1,000,000 times more acidic, would be something with a pH of 1, okay? That's because it's 6 orders of magnitude greater, so it would have a concentration, I'm just gonna make like a division here, 1 times 10 to the power of negative 1 molar, which is the same thing as 0.1 molar hydronium. Okay, so this is more acidic. We can see that as the pH goes down, when pH goes down, acidity goes up. An example of something that would be that acidic would be something, you know, close to gastric juice, which is partially hydrochloric acid. It's 1.6 to 1.8, but just to make the numbers nice and even, we're going to pretend it has a pH of 1, okay? So this shows that, you know, as we increase the concentration of hydronium, the pH is going to go down from 7 to 1. And we can run this in the reverse. Let's look at sodium hydroxide. The pH of that, this will be fun to write out, equals 13. That's equal to 1 times 10 to the negative 13 molar hydronium. Excuse me, I was about to say hydroxide. That's not right. Let me erase that. Hydronium. But you may say, well, sodium hydroxide is a base. Why are we talking about the hydronium concentration? It's a hydroxide donor. Remember that hydronium and hydroxides, they're like complements and opposites to each other. So if we have not a lot of sodium, of hydronium in solution, which is going to be 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 molar, 10 to the 13. We are actually going to have 1 times 10 to the negative 1 hydroxide. Scientists just like to focus on everything in terms of acidity rather than acidity or basicity up to a certain point. All right, so this is what the pH scale is. Boil all this down, we are just looking at the exponent term. That's what we're doing, and ignoring everything else and using that to represent how much or how little hydronium is present in the sample. Okay, And when things are acidic, it's going to have very low pH. When things are basic, it's going to have a very high pH. All right, and what that means, said another way, is that when the power of hydrogen is small, we're moving the decimal place over not very far, like this far, only one place. When it's a very big exponent, we're actually moving it over very far, which means it's going to be very small. Okay, so the takeaway here, I'll say it again because this I know can be confusing, is that the pH scale is a logarithmic scale where we take the exponents of the hydronium ion concentration and use that to as a shorthand to describe if something is very acidic or if something's very basic. And in general, it happens to fall between 0, 1 to 14, but solutions can certainly have a pH below or above this, even negative, but that's just not something we encounter very often. I do not expect you to memorize the pH scale, but just look at it and you'll be able to rationalize this out and be like, okay, grapefruits are very sour. They're going to have a lower pH, something that is going to be below 7, which is neutral. So that makes sense. And we know that ammonia is, a very bitter compound, and that's going to have a pH that's above 7, neutral, which means that it's going to be very basic. Or at the flip side, if something's very basic, it's a very poor acid. Okay? So I hope that makes sense to you. This might be another one of those slides where you may want to rewind and really, make sure that you've got a good grasp of it. But of course, other than that, I'm always available via email, Zoom appointment, or we can elaborate on this, during lab this week. Have a happy Halloween, everyone, and stay tuned for a little bit because we're also going to discuss the results of the mid-course poll in the next slide.